Hello, today we're going to be looking at the exam review for the functions unit. And first let's start off with a little bit of graphing. So for these functions, what we want to do is understand what the parent functions look like, what those graphs are, and then what each of the translations are doing with it. And what will happen with this, we can always just make a table of values if we're having trouble with this. So first here, we've got a quadratic function. We know that it's going to look like a parabola. We've got a point at 0, 0, and then 1, 1, and then negative 1, 1 as well. This minus 2 is going to send it to the right 2. So instead of the point 0, 0, we have the point 2, 0. The negative is going to cause a reflection over the x-axis. So instead of going up like this, obviously that is not what it should be, but it will be going facing downwards, and this is called concave down, but we'll talk about that later on in the course. So our domain, there's nothing that we can substitute into this function that will cause an issue, such as dividing by 0, taking the square root of a negative number, any of that. So we're looking at all real numbers, which is negative infinity to infinity. Remember, we're going to be working with interval notation. Our range for this, it's all of our values for y, so it's all of our negative numbers and 0. So our lowest value is negative infinity, and then our maximum value is 0. We use a bracket because it does include 0. For intervals of increase and decrease, we are looking at where it has a positive slope. So the function has a positive slope here. Now, we're talking about this in terms of our x-coordinates. So I know it might be tempting to say, oh, negative infinity to 0. Don't. That's the y-coordinates. We're looking at x. So it's increasing from negative infinity to 2. We do not include 2 because at 2, that tangent line has a slope of 0, which is not positive, not negative. So it is not increasing or decreasing at that maximum value. So our intervals of decrease then, we start at 2 and go to infinity. Our limit as x approaches infinity of f of x. We're looking at the y-coordinates as x approaches infinity. So that is negative infinity. Same thing when we're looking at as x approaches negative infinity. Right? As x approaches negative infinity, the y-coordinates keep decreasing. Now, we're going to look at an absolute value function. This is going to be the v. The plus 1 is going to send it to the left 1, and the minus 2 is going to send it down 2. So instead of this point at 0, 0, we go left 1, down 2, plot that point, and we know this has a slope of 1. So we plot a couple points. It doesn't need to be all of those. I just do this because I don't have a ruler right now. And so our domain, again, this is going to be negative infinity to infinity because nothing we can substitute in is going to cause an issue that would make it be undefined. So our range, we have a minimum value of negative 2. So we include negative 2 because we have that point 1, negative 2, and we go to infinity. Intervals of increase, it's increasing on this interval. Remember, we're talking in terms of x, so from negative 1 to infinity, decreasing from negative infinity to negative 1. Our limit as x approaches infinity of f of x. So as x approaches infinity, our y-coordinates keep increasing. Same thing as x approaches negative infinity. And there's that one. Now with this, we have an inverse function. So it's going to look something along these lines, a hyperbola, And the key features to graphing this are the asymptotes. We have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. With this one, this -4 is going to send it down 4. It's that vertical shift. But what we'll do is mark it based on the asymptote. We still have the vertical asymptote at x equals 0. So the key with this is starting off with the asymptotes and then understanding that it should be in this section and this section. However, the negative causes a reflection over the x-axis, or more accurately, it's over this line y equals -4, because that's what our vertical shift is. So instead of being here, it's going to come down here and up here. We want generally 1 point to get an idea of what's going on with this. So if we substitute 1 in, so we have -1 plus 4 is 3. So we have, so 1 and then 3. And then we have 2, and then, this would explain why these points are not great. I saw that as a -4. It's a +4. All right, well, we all make mistakes, and that's why we write in pencil. So we look here, we solve the point 1, 3, which makes a lot more sense with what the graph should look like. So it's here, and then we have -1, 5, which is here. So it's close to the asymptote, and then goes on like this. I apologize for that mistake. The +4 is a vertical shift up 4, not down. So our domain and range for this are going to be all of our real numbers except for a specific value. So our domain, we go from -infinity to 0 and 0 to infinity, because we have that vertical asymptote at x equals 0. Our range, same thing, except it's going to be at that value we're skipping is at the 4, where our horizontal asymptote is. Now, with our inverse functions, we're going to have ones that increase over their entire domain and ones that decrease over their entire domain. This is one that is increasing over its entire domain. So the intervals of increase is going to be the same as its domain. Then there are no intervals of decrease. Limit as x approaches infinity of f of x, well, we have that horizontal asymptote at 4. And then our limit as x approaches -infinity of f of x, still approaching that horizontal asymptote at 4. Let's move on. We have a few more functions to graph here. So we've got 1/2 to the x plus 2 minus 4. Now that one is a vertical shift that goes down 4. I'm paying attention this time. So our typical exponential functions have a horizontal asymptote at y equals 0 and then look like this, right? Where they hit the point 0, 1, and then hit the point 1, whatever the base is. But since this base is 1/2, if the base is between 0 and 1, instead it's going to be like a constantly decreasing function with this. We still hit these points, we should still hit the points, let's just graph this, the 1/2 to the x with this. We'll hit 0, 1, and then we'll hit 1, 1/2. We hit -1, 2, and we get kind of an idea of what's going on with this. But then, once we add in our transformations with this. So the plus 2 in the argument is shifting it to the left 2. So it's going left 2, down 4. So you just take these points, left 2 and down 4. Left 2, down 4. Left 2, down 4. And then just move that asymptote from y equals 0 to y equals negative 4. We know it's close to the asymptote, intersects these points. And then continues like that. So our purple one is this graph. Our domain, negative infinity to infinity. Our range, our lowest value is going to be that horizontal asymptote, but we are not going to include that value because it is an asymptote. Our intervals of increase, none. Our exponential are either always increasing or always decreasing. Our intervals of decrease then is the entire domain, so negative infinity to infinity. Our limit is x approaches infinity of f of x. So we're looking here, well, our y coordinates are approaching that asymptote at negative 4. Our limit as x approaches negative infinity, the y coordinates keep increasing, so it's going to be infinity. Okay, so then we have, this is probably the toughest one on the review. We've got the square root of 3 minus x plus 2, and some of you might want to rewrite like this. Whichever way you'd like to look at it is fine. Now, our square root function, we know looks like this. The plus 3 is going to send it to the left 3. The plus 2 is up 2. But then the negative with the x is going to reflect over our y-axis. Okay, so we're going to take this point 0, 0 and perform those transformations on it. So we go left 3. So we go left. Ooh, remind me later, please. We go left 1, 2, 3. We go up 2. But then we have to reflect over the y-axis. So instead, it looks like we moved to the right 3. Okay. Now, instead of it swooping this way, I know that's the technical term for our square root, it's going to instead, that has gotten reflected over the y-axis. So let's substitute some other points in with this to help us graph. So we can just go through, make a table. If we substitute, say, this is f of x again. If we substitute 4 in, we end up with taking the square root of negative 4 plus 3 is negative 1 plus 2. We can't do that, right? We're graphing on an entirely real graph right now. Whereas let's substitute in negative 1. And honestly, that's the only other point we really need. You can do others, but with those two, you get an idea of what the graph is supposed to look like. So we substitute negative 1 in, and get square root of 4 plus 2. So we have this point, negative 1, 4. Okay, so that's approximately what it is going to do. Now, here, our domain is going to be negative infinity up to 3. We're going to put brackets on 3 because with our square root, we do include that value. Our range goes from 2 to infinity. Remember, it always goes least to greatest. Again, we're including the 2. Intervals of increase, nope, none. And then it's decreasing over its entire domain. Now, the reason we include 3 and we didn't include 2 in our parabola was that the function is still decreasing at x equals 3. So picture our roller coaster example. You've got a roller coaster car riding along this function, and the track ends at x equals 3. It's still decreasing. Not a safe roller coaster, but it's still decreasing. So our limit as x approaches infinity of f of x does not exist. The function's not doing anything as x approaches infinity. So we can't say what the limit is. Same idea, who did you vote for in the 1980 presidential election? None of us were alive, so we couldn't have voted in it, so does not exist. Limit as x approaches negative infinity is infinity. All right. Log of x plus 5. Only one translation on this one. So we take a look. Our logarithmic function, it's our inverse of our exponential function. So we know that we have a vertical asymptote at x equals 0. We hit the point 1, 0. And then we hit the point, whatever the base is, and then 1. It's the inverse of our exponential function. So in this case, our base is 10. So we should be hitting the point 1, 0, and then 10, 1. But the plus 5 is just going to shift that up 5. So our asymptote stays the same. Okay, we have that vertical asymptote at x equals 0. Now, instead of the point 1, 0, we just have the point 1, 5. Because that's just been shifted up. Instead of the point 10, 1, we have the point 10, 6. And then we know that our logarithmic functions just kind of get very close to the asymptote and slowly increase towards infinity as x approaches infinity. So as x approaches infinity, our asymptote, or our limit, is infinity. Domain, we skip 0, but it's all of our values greater than that. Our range is all real numbers, so we'll go from negative infinity to infinity. Just like with exponential functions, our logarithmic functions are either increasing or decreasing on its entire domain. So this is increasing from 0 to infinity, and it is not decreasing. Just like our last problem, limit as x approaches negative infinity of f of x does not exist because the function isn't doing anything as x approaches negative infinity. Next, let's start taking a look at some inequalities. So our polynomial inequalities, we're going to solve using sign charts. So our first one here, what we're going to do is factor. So this we can factor by grouping once we split it up a little. So we look at the factors of 3 and 10, so we get 30. And so we look at that, 1 and 30, 2 and 15, 3 and 10, 4, 5, and 6. So we're going to split this up into 3x squared minus 6x plus 5x minus 10. Then we can factor by grouping. So 3x squared minus 6x, we can factor out a 3x. 5x minus 10, we can factor out a 5. Then we factor out an x minus 2, so we have x minus 2. And then 3x plus 5 as our factors. So we know that that is greater than 0, and we will make our sign chart in part 2.